So we could also come up with a solute activity. And what's important to note that the activity always equals 1 for a pure solid or liquid. This is going to come up when we get into equilibrium, and it's part of the reason why we don't include pure solids or liquids in equilibrium expressions, because their activity equals 1. That's kind of what we were talking about here. As our solution becomes more and more dilute to the point where it's now no longer a solution, but it's just a pure liquid, the activity will be 1. Well, the same is true for a pure solid as well. Okay, the activity is always 1. All right. But if we have now in a solution, okay, and this is the case of an ideal solution, the solute will follow Henry's law, like what we talked about before. So now I'm going to say AB, where now B is my solute, and that's going to be the observed pressure of that solution divided by the Henry's law constant. Okay? And that's dependent on which solvent you are in. Okay? And our limits for the solute go as the following. So AB will approach 1 as gamma B approaches 1. So that's just basically saying as the solution becomes more and more dilute, or as you approach that of a pure material, the activity will become 1. But this is different from the solvent case. The mole fraction here now approaches 0. So in the solvent, the mole fraction was approaching 1. However, in this case, the mole fraction of the solute is approaching 0. So it's more or less saying the same thing that we said before. And so now we can come up with activities in terms of all kinds of different concentrations. So again, this is just vapor pressure. But what about other activities? So we can come up with activities in terms of molalities. I always have to say this out. Molalities. Okay. And so I'll use a J to indicate chemical species J. And so that's going to be, I'll use a B for molality. That'll be the molality of species J divided by standard molality, okay? Where standard molality is exactly 1 mole per kilogram. Of course, we could do this for molarities. And in terms of molarities, this would be then, the molarity of species J divided by standard molarity, where standard molarity is, of course, 1 mole per liter. And then in terms of partial pressures, it's the same as this. So partial pressures, then the activity it's just exactly like what we kind of described before, except for in terms of standard notation, it's the partial pressure of species J divided by standard pressure, where standard pressure is typically 1 bar. Now, the reason why we have all of these is because, as we will see, this is going to become the basis for equilibrium. So when we talk about equilibrium, you've been used to seeing it in terms of partial pressures or molarities, but technically equilibrium is in terms of activity, as we shall see. So this is creating the basis of how we can use activity for equilibrium in various concentration or pressure units. So in terms of partial pressures, in terms of molarities, or in terms of molalities. So basically these activities, in this case now, are becoming a dimensionless quantity, right? We're ratioing it to whatever standard base unit, okay? And the last form of activity